In 2012, the Arecibo Observatory in Puerto Rico detected something that defied explanation: a burst of radio waves, brighter than anything ever seen, lasting less than 5 milliseconds, coming from a galaxy 3 billion light years away. And then it happened again, and again, and again. This wasn't supposed to be possible. Fast radio bursts, one-time events, cataclysmic explosions, neutron stars colliding, black holes merging, things that destroy their source in the process. But FRB 121102 kept repeating. Over 200 bursts detected to date, each one releasing as much energy in a single millisecond as our sun produces in an entire day. Astronomers had two choices: rewrite everything they thought they knew about these cosmic flashes, or consider something even more unsettling. What if this signal wasn't natural at all? Fast radio bursts were first discovered in 2007, buried in archival data from the Parkes Radio Telescope in Australia. The Lorimer burst was a single flash lasting just 5 milliseconds. The signal's dispersion told astronomers it came from billions of light years away. Over the next few years, more FRBs were detected, all incredibly bright, impossibly brief, and seemingly random. Most importantly, none of them repeated. This made sense. The energy required for an FRB suggested the source destroyed itself in the process. Neutron star collisions, supernova explosions, events that could only happen once. In November 2012, Arecibo detected a fast radio burst coming from the constellation Auriga. Strong signal, typical duration, massive dispersion. Just another FRB to catalog. 3 years later, astronomer Paul Schultz at McGill University was examining archival Arecibo data when he found something impossible. 10 more bursts. Same dispersion measure, same location in the sky, all consistent with the original FRB 121102. The source had survived, and it was still broadcasting. This single discovery eliminated an entire class of explanations. Whatever FRB 121102 was, it wasn't a one-time cataclysmic event. It wasn't a neutron star collision. It wasn't a supernova. It was something persistent, something active, something that could produce these extraordinary bursts again and again without destroying itself. And that's when things became truly strange. Once astronomers knew FRB 121102 repeated, they pointed every available telescope at its location. What they found challenged physics itself. The bursts weren't just bright, they were twisted, almost 100% linearly polarized, with the polarization rotating as the signal traveled. This effect, called Faraday rotation, happens when light passes through a magnetic field. The rotation measure for FRB 121102 was staggering. In the source's reference frame, accounting for its distance, the rotation measure exceeded 100,000 radians per square meter. That's 500 times higher than any other FRB ever detected. To put this in perspective, such extreme Faraday rotation has only been observed in two places: near the supermassive black hole at the center of our galaxy, and around magnetars in extreme environments. FRB 121102 wasn't just somewhere unusual, it was somewhere that shouldn't exist. Using the Very Large Array in New Mexico, astronomers pinpointed the source's location with milliarc-second precision. The bursts originated from a dwarf galaxy 3 billion light-years away, a tiny, star-forming galaxy with unusual properties. But here's what made astronomers stop cold. Right next to the bursting source was something else. A compact, persistent radio source. Not bursting, just glowing steadily. The bursts and the persistent emission were co-located within 40 parsecs, about 130 light-years. They were physically connected. Part of the same system. No known object produced both repeating millisecond bursts and steady radio emission. Whatever FRB 121102 was, it was something entirely new. Then, the rotation measure started changing. Between January and August 2017, the Faraday rotation measure for FRB 121102 decreased by about 10%. That's a massive change over just 7 months. But more detailed observations revealed something even stranger. The rotation measure didn't decline smoothly. It jumped around erratically, varying by thousands of radians per square meter over timescales of weeks, sometimes even days. This told astronomers that whatever environment surrounded the source, it was dynamic, turbulent, constantly changing on timescales that challenged every model. The numbers constrained the possibilities. To produce that much Faraday rotation required extremely strong magnetic fields comparable to those near supermassive black holes or within the remnants of recent supernovae. It also required dense plasma. Lots of free electrons swirling through intense magnetic fields, an environment more extreme than anything observed around normal stars or even most neutron stars. 2 scenarios emerged. First, a young magnetar embedded in a supernova remnant. Magnetars are neutron stars with magnetic fields so powerful they dwarf anything else in the universe. The bursts could come from starquakes or magnetic reconnection events, the persistent radio emission from electrons spiraling through the surrounding nebula, the changing rotation measure from the expanding remnant gradually thinning out. Second, a neutron star orbiting near a massive black hole. Black holes warp space-time and create accretion disks swirling vortexes of superheated gas with intense magnetic fields. A neutron star passing through these regions could trigger bursts during each passage. Both models explained the observations, but neither explained everything. And then, in 2020, something unexpected happened. Astronomers monitoring FRB 121102 with the FAST telescope in China noticed a pattern. The bursts occurred in windows, active periods lasting about 90 days, followed by silent periods of similar duration. The cycle repeated roughly every 157 days. This was unprecedented. None of the other known FRBs showed this behavior. But once astronomers knew to look for it, the pattern became clear. During active periods, dozens of bursts. During quiet periods, complete silence. The source would go dark entirely, then wake up again right on schedule, as predictable as clockwork. Multiple research teams confirmed the periodicity. The cycle wasn't perfect. It varied slightly, suggesting complex dynamics, but it was undeniably real. Periodicity meant orbital mechanics. Something about the source's environment changed on a 157-day timescale. Perhaps it orbited something massive. Perhaps its orientation changed as it precessed, because the bursts themselves were becoming stranger. In 2019, astronomers detected 1,652 individual bursts from FRB 121102 over just 47 days. At peak activity, the source was producing 122 bursts per hour. Analyzing these bursts revealed something unexpected. The energy distribution was bimodal, 2 distinct peaks with a gap between them. This suggested 2 different emission mechanisms, or the same mechanism operating in 2 distinct modes. Either way, FRB 121102 was more complex than anyone had imagined. The bursts also showed extraordinary variety. Some were simple, a single sharp pulse. Others were complex, with multiple peaks and substructure on microsecond timescales. The shortest features lasted less than 30 microseconds, constraining the emission region to be smaller than 10 kilometers, about the size of a neutron star. Everything pointed to a compact object, a magnetar, most likely. But no magnetar in our galaxy behaved like this. And that raised an uncomfortable question. What if FRB 121102 wasn't a young magnetar at all? What if it represented something we hadn't even considered? The question hung in the air, unanswered. Could the signal be artificial? Could it be a beacon from an advanced civilization? Some scientists calculated that FRB 121102's energy output matched theoretical predictions for alien spacecraft propulsion systems, massive directed energy beams pushing light sails to relativistic speeds. But the hypothesis had problems. The burst's extreme polarization suggested natural magnetic fields, not artificial beamforming. The changing Faraday rotation implied an astrophysical environment, not empty space. Most tellingly, the bursts showed no coherent pattern, no embedded information, no modulation, just raw electromagnetic energy. SETI researchers found nothing suggesting intelligence. The signal appeared natural, but natural didn't mean understood. More than a decade after its discovery, FRB 121102 remains incompletely explained. The magnetar model remains the leading hypothesis. A young, highly magnetized neutron star embedded in a supernova remnant explains most observations. The extreme Faraday rotation, the persistent radio source, the millisecond burst durations. But critical questions remain. Why does FRB 121102 repeat when most other FRBs don't? What triggers the individual bursts? The 157-day periodicity still lacks a satisfying explanation, and the bimodal energy distribution suggests a complexity current theories don't capture. Perhaps most frustratingly, we don't know if FRB 121102 represents all FRBs or if it's a special case. In 2020, an FRB was detected within our own galaxy, coming from a known magnetar. That seemed to confirm the magnetar hypothesis, but that burst was thousands of times weaker than FRB 121102. And it came from a magnetar that had never produced an FRB before and hasn't since. The universe, it seems, isn't offering easy answers. FRB 121102 transformed how we think about the universe. Before its discovery, fast radio bursts were curiosities. Mysterious? Yes, but ultimately straightforward brief flashes from cataclysmic events, interesting primarily as probes of the intergalactic medium. The repeating bursts changed that. They revealed that somewhere in the cosmos, something creates these extraordinary signals repeatedly, survives the process intact, and operates in an environment more extreme than almost anything else known to science. The source forced astronomers to expand their models, to consider scenarios they'd never imagined, to accept that nature produces phenomena stranger and more varied than our theories predicted. And FRB 121102 did something else. It showed us that even in an era of powerful telescopes and sophisticated instruments, the universe still holds genuine mysteries. Not gaps in our knowledge that will be filled with routine observations, but fundamentally new phenomena that challenge the very foundations of our understanding. Somewhere, 3 billion light-years away, in a dwarf galaxy we can barely resolve, something continues its enigmatic broadcast. It pulses and pauses, follows patterns we're only beginning to recognize, operates in an environment we can barely characterize, and produces energies that strain the limits of what physics allows. We've ruled out cataclysm, we've ruled out coincidence, we've likely ruled out aliens, but we haven't solved the mystery. Because nothing about the signal that keeps repeating is normal. And perhaps that's exactly what makes it extraordinary. The universe doesn't owe us simple explanations. FRB 121102 is proof of that. And somewhere in the darkness, it's still broadcasting.